This is something we did not talk about in class, but it's still relevant and it's stuff you should still know or be able to do. So this is an introduction to rotational motion. It's the motion when something is spinning around, like rotating about an axis. The good news is there are clear connections from stuff we already know, translational motion, to the stuff we want to know, which is rotational motion, also called angular motion. So first of all, we're going to learn to translate symbols. The symbol for displacement, the generic symbol for displacement, with translational kinematics is delta S, change in spatial location. With velocity, we have V. And we know there's multiple flavors of V, right? There's V initial, V final, delta V, and average V. All right, so I just want to point out that there's not just one V. Just like up here, there's a final position and initial position. Those are all things related to displacement. All right, I just wanted to point that out. Although that bothers me the way that it looks. Okay, acceleration. Acceleration is A, and time is delta T. That's the only scalar quantity in the group, so direction doesn't matter for time. Rotation looks a little worse, but the concept is the same. The concept of displacement is the same. It's a change in position, but rotationally, we have angle measures instead of meters. Velocity is still velocity. It's still the rate of change of position with respect to time. But the symbol looks like a lowercase w. It's an omega. It's a lowercase omega, just so you know. It's Greek. Acceleration is a little fishy symbol. It's an alpha. And time is still time. All right, so now we have translational and rotational quantities. We have symbols for them. I'm going to show you how they all go together. Or, you'll see. So our kinematics equations, the big four. Displacement equals 1/2 acceleration time squared plus initial velocity times time. Now, I didn't say anything about linear crap there. I said displacement equals 1/2 acceleration time squared plus initial velocity times time. Now watch this. Displacement equals 1/2 acceleration times time squared plus initial velocity times time. It's the same relationship. The only thing that's changed is now we're talking about angular quantities or rotational quantities instead of the translational ones, the linear ones. Okay, here's another one. Listen. Average velocity equals displacement over time, or initial velocity plus final velocity over 2, provided, of course, that we have constant acceleration. Again, average velocity equals displacement over time, or initial velocity plus final velocity over 2, provided that we have constant acceleration. Acceleration, change in velocity over change in time. Acceleration equals change in velocity over change in time. And finally, everybody's favorite, VF squared equals VI squared plus twice A delta S. Or final velocity squared equals initial velocity squared plus twice acceleration times displacement. Final velocity squared equals initial velocity squared plus twice acceleration times displacement. The four equations are the same. They say the same thing. It's just they're relating translational quantities or rotational quantities. You just keep them separate. All right, so hopefully you're not terribly intimidated, although the equations do look a little bit worse. Some other information you'll need to know is how do we go, or how do we relate from translational to rotational. Now, let me see, how's this going to go? Hey, a circle. You could, it's sort of a circle, you could have some position on that circle. So let's suppose you are right here. That is your position. With rotational quantities, we could describe that differently. Your position is the radius away from the center of the circle, pointed at an angle theta. Just so you know, with units, position is in meters, radius would be in meters, the angle measure would be in radians. And this is a big deal, because radians are kind of a non-unit. So I have meters equals meters times a non-unit. So dimensionally, or based on units, I'm good. If you started here and you had some initial position, and this is some final position, then we'd call that a displacement and a change in angle. But the units don't change at all. Now, if you remember, velocity is the rate of change of position with respect to time. It's an integral, or sorry, it's a derivative. It's the slope on a position versus time graph. We could do the calculus or not. Instead, I'll just tell you velocity relates to omega that way, and acceleration relates to alpha that way. In general, the translational quantity equals the radius times the rotational quantity. Although this equation up top there, that's absolute nonsense. So let's maybe get rid of that. More important would be recognizing this piece here, and this piece here, and this piece here. Again, looking at units, I have meters per second, and that's going to equal, let's see, radius is in meters, and omega should be in radians per second. Now remember, that radian is a non-unit, so I have m times nothing over s, so meters per second. Similarly, meters per second squared equals meters radian per second squared. So still dimensionally it works out. The reason I'm pointing that out is because sometimes rotational quantities are given in different units, just like translational ones could be meters per second, miles per hour, kilometers per hour, or any of those sort of things. Rotationally, we could talk about revolutions, or like RPMs, or we could talk about radians per second, or radians. So for these equations to work, we need to be in radians, radians per second squared for this page to work. The kinematics equations we just showed, those will work for any self-consistent set of units. So you could do rotations per minute and rotations per minute squared. As long as your entire set of units is dimensionally consistent, you'll be fine. But for translational equals R rotational, we need to be in radians. All right, so how would a problem look? Let's take a look. Nope. Same strategies apply with the tables. So if you were given an initial velocity and a displacement and a time, you could solve for this thing. Same table of 5 in theory, same basic approach. Like if I wanted to solve for this final velocity, final rotational velocity, and I don't care about acceleration, I would pick the equation that doesn't have acceleration in it, which would be average omega. And rearrange that for whatever I wanted. So that process is the same. A question like this might be related to your computer hard disk. When you turn your computer on, you might hear the hard disk spinning or the drive spinning. It'll boot up to some final RPM and some number of rotations in some amount of time. So that would be a context here, or a bike tire spinning around, or your car tire. There's another type of problem that might look like this. Now, if you recall, a table of 3 is when acceleration is 0. Context here, your microwave probably has a turntable. When you turn the microwave on, it just starts spinning. It doesn't speed up as it spins, and it doesn't really slow down as it spins. It just spins at a constant rate. So a table of 3 might be appropriate there. Or if a tire was rolling across a surface, pretend that's a flat surface. If that ball's not speeding up, right, if its velocity is constant, then its omega would be constant as well, because acceleration would be 0. So that's two different contexts where we might solve a problem, and we use exactly the same process. One difference, though, that I do want to point out, and I want to make as clear as possible, is our freedom with coordinate systems. With translational things, I've always given you freedom to say whichever way you want is positive. And that's been fine, and everything has been according. Your answers are always according to whatever your coordinate system is. Rotational stuff is different. Rotational, you don't get to decide. With rotational stuff, counterclockwise is positive. And that's going to be consistent with our unit circle. And anything clockwise, then, you need to know is negative. So that's pretty much it. You should be able to read a rotational motion problem and then dump the information into the tables, choose appropriate starting points based on the same strategies we always have, and solve accordingly. Doesn't mean it's going to be easy. It will look a little weird. The symbols are a little gross, but conceptually it's no different than translational motion. Yeah, that's pretty much it. If you wanted to practice this, let's see, Physics 121, folks. This is Chapter 4, latent Chapter 4, like Section 6 or 7. And then 111, folks, this is maybe Chapter 10 in your book. And it only does it very briefly before it gets into nastier stuff. But this is the basics of rotational kinematics. Peace out.